Good afternoon, ladies and gentlemen. My name is Felix Sutton, and I'm very happy to present to you our work entitled BOLT, a Stateful Processor Interconnect. This work was performed at the Computer Engineering Group at ETH Zurich under Professor Lothar Thiele. If we look back at the last 10 to 15 years of wireless sensor network research, the most predominant platform that's been in use is the Classical Mote architecture. And this has been a very successful platform and has produced an extraordinary amount of research contributions. This architecture consists of a single processor, interface to arbitrary sensors, and also a radio or communication interface. Now, this particular platform architecture has been very successful for sense and send style applications, where we periodically extract data from our sensors, perform some local processing before communicating this through a network. However, we're seeing a change in the application landscape towards more sense and react style applications, where we have more complex sensors, multimodal perhaps sensors, event or periodic based sensors, and also more complex communication protocol stacks that are introducing significant challenges on the single core processor. Not only is this placing increased resource demands on our single core processor, it's also providing or enforcing hard real-time constraints on our core, particularly due to advanced communication protocol stacks. This poses several challenges to the system designer. The system designer must deal with the complexities of running concurrent tasks on a single core, where each of these tasks compete for shared resources in terms of memory, CPU, and peripherals. Secondly, the state space is increasing. With more state machines, the state base grows, creating difficult or tedious to implement software, difficult to debug, and also very difficult to incorporate optimal power management strategies. Furthermore, it makes it very difficult, if not impossible, to give runtime guarantees on our platform. In order to mitigate some of these effects, we are seeing trends towards multi-processor platforms, whereby we map the application tasks onto a dedicated application processor, and similarly we map the communication protocol stack onto a dedicated communication processor. Now clearly these two cores need to share information, and they do this through a processor interconnect. If we're not careful on how we implement this processor interconnect, we actually introduce interference in terms of the processor's time, power, and clock domains. To understand this a little further, let's look at the main techniques that are used to interconnect these two cores. The first of which is a shared bus. It's a stateless interface, meaning that the state of the bus is managed by both application and communication processor. And this shared bus links these two cores in time, power, and clock domains. To give an example, if the application processor wants to send a message to the communication processor must stop what it's currently executing in order to receive the message and process it, therefore linking the two cores in the time domain. If the communication processor, however, was in a deep sleep mode, it would actually have to be forced to wake up into an active mode in order to receive this message and process it, thereby linking the two cores in the power domain. Furthermore, these two cores would also have to agree in advance on a clock frequency in order to share messages across the shared bus, thereby linking them in the clock domain. A popular alternative is to use shared memory, and essentially a shared bus with some memory that's addressable by both cores. Because we also have a shared bus, we still link these two cores in time, power, and clock domains, while it also is a stateless bus. A stateless interconnect, since the application and communication processor must manage the software structures that enable message transfer between the two cores. Our approach, however, is a stateful processor interconnect, whereby we use dedicated bus, which interfaces to an intelligent memory interface, or memory block. And we call this memory block BOLT, a stateful processor interconnect, and we're able to decouple these two processes in the time, power, and clock domains using asynchronous message passing between the two cores. What's more important, or even more important, is that we're able to perform this asynchronous message passing with predictable timing properties. Now, BOLT is a combination of hardware and software that sits in between these two arbitrary processes, consisting of a message controller, which manages two FIFO queues, one for each message flow. And these message queues reside in non-volatile memory. And so we're able to decouple these two processes in the time and power domains, since each processor is free to read and write messages according to its local execution policy. And similarly, they're able to operate in their own clock domains, since they have dedicated control and data buses. The main architectural benefits of Bolt are twofold. Not only are we allowed to, the first of which we're able to provide predictability. Predictability in terms of we can precisely define the worst case execution times for reading and writing messages, which allows both processes to safely schedule message transfers. Secondly, we provide composability to the architecture. And this allows arbitrary selection of application and communication processes and interconnect them without affecting the integrated parts. And we will come back to these two properties in the evaluation later. So how did we build Bolt? So we followed three design principles that are familiar in the embedded systems community. First of which, wherever possible, we must avoid resource interference. If, however, there are circumstances where we can't avoid this resource interference, we tightly bound it. And lastly, we specify an interface with formally verified properties. And so we applied these three design principles to implement a prototype of Bolt based on an MSP 430 state-of-the-art microcontroller, which also incorporates non-volatile FRAM built in. So in the next few slides, I will go through each of these design principles in depth and explain how we applied them to our prototype, starting with how we avoid resource interference. So we firstly avoid resource interference by allowing messages to be performed on a control and data interface which are dedicated to each processor. And more importantly, we map these control and data paths onto independent hardware blocks within our microcontroller. So we use independent GPIO ports, independent SPI and DMA to provide the message transfer. And so we'll take a closer look now at what these data and control interfaces look like. And here we see a breakdown of the GPIO pins that we use to provide the control path and then the data path. Firstly, we use a single GPIO pin to define the type of message or type of operation, whether it be read or write. Then we use a request and an acknowledgement pin to provide a four-way handshake for a processor to request control over the SPI data transfer. And lastly, an indication pin that provides information to the processor that at least one message is available to read out. The data path is implemented using a standard 3-wire SPI bus, with the important factor is that Bolt is always the SPI slave, allowing each of the processors to drive the clock of the SPI bus. So now we've avoided the resource interference wherever possible, we now seek to tightly bound any unavoidable resource interference. And indeed, we have unavoidable resource interference, particularly when we have simultaneous message operations. An example illustrated here, when the application processor writes a message in, while the communication processor simultaneously reads a message out of this FIFO queue, we encounter resource interference on our Bolt implementation, both in terms of software and in terms of hardware. And we'll look at these two cases individually. The Bolt software state machine is purely interrupt driven. And this figure illustrates the microcontroller's execution over time with respect to a message operation, which is driven by the four-way handshake. During no operation, or when there's no message to transfer, our microcontroller is in deep sleep, LPM mode 4. And when, during the four-way handshake, this triggers an external interrupt on our microcontroller, we perform the necessary setup of the internal peripherals and memory using a GPIO interrupt service routines. During the actual message transfer, the microcontroller resides in LPM 0 mode while the DMAs are active. And then lastly, the handshake completes the message transfer, again triggering a GPI ISR before the microcontroller returns to a deep sleep mode. Similarly, a read operation is very similar, with the difference being that a DMA ISR is what's triggered to the commit phase of a read operation. And as we can see, if we perform write and read operations simultaneously, these interrupt service routines will compete for CPU execution, essentially causing resource interference on our microcontroller. A second aspect is hardware interference that we see on Bolt. And this is primarily due to three independent reasons. The first one is that the microcontroller imposes a fixed priority scheme for all interrupts. So we see that the port interrupts for 3 and 4 on the GPIO port, where 3 has higher priority than port 4. Similarly, the DMA channels also have, DMA 0 has a higher prior than DMA 1. So when the interrupts occur simultaneously, clearly one ISR will be executed in preference of the other. Also, we perform all data transfer is handled using DMA towards, from the SPI modules to the internal FRAM. And the DMA stalls the MCU for precisely 2 clock cycles per byte transfer. So this also has to be factored into when we want to evaluate or determine tight worst-case execution times of read and write operations. And lastly, we have non-deterministic wake-up delays on our microcontroller. So contrary to what most datasheets provide or specify, the wake-up times between, for example, LPM4 to ISR execution, or indeed the end of a DMA operation, actually have a very highly non-deterministic execution time. And these are 2 examples where we characterize these delays using a logic analyzer on our prototype. And so we need to factor not only the software interference, but also the hardware interference in order to define the worst-case execution time for our read and write operations. In order to do this, we use or apply a formal method. So we first constructed a model of the MSP430 CPU using information available in datasheets and user guides, etc. And here we see the GPIO block for the 4-way handshake. The SPI and DMA channels are handled by DMA controller, internal FRAM, and the MSP430 core. So we mapped this model into UPPAAL, which is a very popular and very widely used timed automata model checker, and we're able to construct what ended up being quite a complex model consisting of more than 9 automaton, where we modeled each of the hardware and software interactions going on within Bolt. It consisted of more than 120 states, more than 160 transitions, but it allowed us to then query the model checker in order to determine worst-case execution times for our operations. And as we'll see in the evaluation later, we achieved very tight timing conditions. So we've seen how we avoided resource interference and how we try and bind this unavoidable interference using formal methods. We lastly specify an interface with formally verified properties. And so there's multiple parts to this. So we first specified the message operations themselves, and we do this using the 4-way handshake I introduced earlier. And again, we have an indication pin that a processor is able to look at to determine whether there's at least one message waiting in the Bolt queue to be read out. And so we modeled this 4-way handshake in UPPAAL, and we're able to use the model checker to determine whether there are or are not deadlocks in given a valid input sequence. And using a model, we're able to prove that given a valid input sequence, we're able to prove no deadlock occurs. Now, Bolt also incorporates non-volatile memory, and this allows message consistency to be performed during a power-up or reboot of the Bolt hardware. And this allows us to, by placing all of the state and message queues in non-volatile memory, we're able to remove partially written messages and also retain partially read messages as part of a message consistency feature. Now, because we provide asynchronous message passing, we must prevent non-blocking writes. Otherwise, we're not able to provide this asynchronicity between the 2 cores. And there are 2 schemes in which this is possible. In the case where we treat all messages with the same priority, we can simply dimension the Bolt queues internally and also the receive buffer on each processor according to the expected dynamics of the application. In the scenario where we want to incorporate multiple message priorities, for example, in a protocol stack, control type messages might have one priority versus data type messages might have another. We introduced a concept in our paper, the details of which you will find in our paper, called virtual queues, where we're able to reduce the complexity of this multi-priority problem into that of a single message priority problem, and then dimension accordingly. So now we've seen how we applied the design rules in order to construct our prototype. We now look at evaluate the key architectural benefits of Bolt, and we first look at predictability. So in order to determine experimentally the predictability of Bolt, we essentially stress tested Bolt by interconnecting it to a communication and application processor, and used a logic analyzer to measure the commit phase timing properties of the 4-way handshake, and the request phase of a message transfer, read and write transfers simultaneously. So we also set up not only simultaneous message operations, but also random inter-arrival times of these message operations to really force worst-case conditions on Bolt. And here in this plot, we illustrate a histogram for the request phase for the port 3 towards the application processor, port 4 towards the communication processor for both request and commit phases. And the first thing to highlight is that we see in the worst, and x-axis is the number of the worst case, or the execution time in terms of microcontroller clock cycles. The first thing we see is we observe the port prioritization between port 3 and port 4, whereas the worst case execution time for the commit phase, which is dominated by DMA, is the same because DMA stalls the microcontroller for the same amount of clock cycles, independent on the port. What's most interesting here is that these dashed red lines are the worst case execution times extracted from our formal method. And we see that we achieve extremely tight worst case execution, in fact worst case of 12 clock cycles greater than what we measured experimentally. This is a very impressive result and allows the application and communication processor to use this information to safely schedule message transactions. Next to the composability property of Bolt. To give more of a formal definition, the composability property ensures that when you integrate components, that you're able to integrate components without changing the properties of the integrated parts. To give a graphical example, I have an application and communication processor with some predefined task scheduling processing, and then when I interconnect them, of course, I have some overhead in terms of message transferring, but we don't impact the existing application processing of each of the processes. The overhead is not only low, but the overhead is predictable. And this gives great benefits to the system designer, as it gives great flexibility in selecting arbitrary hardware components that best suit the application domain and the communication domain. And it makes it easier to implement and debug software and components in isolation, furthermore promoting hardware and software component reuse, and we believe will improve overall system maintenance. If you saw our demo yesterday, we demonstrated a few of these application communication processors, essentially exhibiting the composability property of Bolt. So we then looked at a concrete case study for event-driven wireless sensor networking, where we interconnected a state-of-the-art 32-bit ARM microcontroller running at 72 megahertz to a state-of-the-art 16-bit system-on-chip radio CC430 interface with Bolt. What's important to notice here is that they're both running at very different clock cycles. We're running 72 megahertz, 20 megahertz, different message lengths of 48 and 24 bytes respectively, and different SPI frequencies of 4 and 2 megahertz respectively. And so we evaluated this example wireless sensing prototype using a power analyzer for both for the ARM, the CC430 and Bolt itself, during a write operation from the ARM side and a read operation from the system on chip. And what's important to highlight here is that during periods of inactivity, Bolt only dissipates 1.3 microwatts, which is really negligible in terms of the active and sleep power dissipations of the interconnected microcontrollers. And actually during a read or a write operation, we dissipate 1.1 milliwatts, which concurs with the data sheets of our microcontroller. We analytically evaluated the number of messages we can support in our current prototype, and assuming a 16-byte message length, we can provide more than 1,000 messages in each of our queues. And we experimentally evaluated the average throughput of message transfers, exhibiting up to 3.3 megabits per second, assuming 128-byte message length. So in summary, we introduced an ultra-low power processor interconnect that decouples processors in time, power, and clock domains. We really see this as an architectural footprint for the composable construction of future predictable heterogeneous sensing platforms. We evaluated Bolt experimentally, exhibiting a very predictable runtime behavior, comparing the experimental results with a formal method. We measured power dissipation of 1.3 microwatts during periods of inactivity and up to 3.3 megabits per second message throughput. And we would very much appreciate if you look at our website, where we've provided all of the design material to construct your own bolt, and hopefully to construct your own heterogeneous wireless sensing platforms. That concludes my presentation, and I'm very happy to answer any questions you have. Thank you.